Hello Chem students, this is going to be the first lecture of 3 on chapter 10, which is a new way of thinking in reactions. We're going to look at free radical reactions. These are pretty different than the polar reactions we've been looking at, but are going to be very important for our course. Okay, so we're going to emphasize two different types of free radical reactions. One of them will be what we call halogen substitution reactions, and that'll occur at sp3-CH bonds. Okay, we're going to take an H off and put a bromine on, so it'll be a switch. The other reaction we're going to look at is called free radical addition of HBr to an alkene pi bond. So you'll notice there's a degree of unsaturation here, and we'll add a H to one carbon and a Br to one carbon. Okay, so both of these reactions go by a three-step sequence. It starts off with what we call initiation. So we'll begin it by input of energy. We'll always use light, but also heat is possible. And then we'll look at a sequence of two steps called propagation. So these will go on and on and on, sort of a chain reaction that can last for hundreds to thousands of times. So we'll have a 2A and then a 2B and then back to 2A and 2B. And ultimately, two of the free radicals will find each other, and we'll call that termination. That will stop the reaction. However, there's always new reactions beginning because we're always initiating with the input of light. Okay, so both of these reactions that we look at up here will follow this sequence, but it's slightly different pathways. The reactions are very important because they are regioselective, meaning a specific region of the reaction, specific region of the structure reacts. And so they're very predictable, and that's going to be good for us in terms of making molecules, simple molecules in our synthetic approaches. Okay, so we have two types of bond breakage that we could look at. One's called homolytic, like what we're talking about here. Homo means same, lytic, cleavage. And so we're going to take a bromine, in one reaction here, we're going to take a bromine and split it equally into two bromine atoms. A bromine molecule becomes two bromine atoms. So that's going to cost us energy. For a bromine, it's a pretty low cost. It's about 46 kcal, which can even be done with visible light. Okay, so we're going to be using these bromine atoms in this chapter. Heterolytic bond cleavage is more like what we've been doing. So if you think back to the last topic, chapter 9, when we did SN1 and E1 reactions, the first step was the bromide left, and we were left with a carbocation, so this had to be either secondary or tertiary for that to work back then. But this would be a heterolytic cleavage where one guy gets both the electrons and one guy loses them both. That's pretty expensive energetically, and for this kind of reaction you need something polar, a polar solvent, so we used water and alcohols as our solvents. Other possibilities exist, but that's what we used. Okay, so our first type of reaction is free radical substitution of sp3-CH bonds. We're going to switch the H out and put a bromine in. It goes by those three steps that I just mentioned: initiation with light, propagation, two steps, and termination. Okay, the bromine will take the place of the hydrogen atom. And what we're going to find, now this is a complicated molecule. It doesn't look that complicated, but it does have a lot of different types of hydrogen. So we got a methyl out here. That's a primary carbon. I got a tertiary here, and I got a whole bunch of secondaries around here. And one reason we like this reaction so much is when it works, it's going to pick out, even though there's only one of them, there's only one tertiary CH, that's going to be the main product. Okay, so because it's so predictable, we can use this in a very useful way. Okay, so the other halogens are possible. Chlorine could do this, but chlorine is not real selective. It's so reactive, it tends to attack all the positions. Still, tertiary is best, secondary is second best, and primary is third best, but they're pretty equal in concentration, whereas bromine really selectively goes after that tertiary spot. Fluorine could work, except fluorine is too reactive. If you mix fluorine with an alkane, you probably get an explosion. It's so reactive. And then iodine is so sluggish that it's not really useful, at least to be practical. Okay. The second type of reaction we're going to look at is free radical addition to an alkene. So here's our alkene. And you'll notice this is an unsymmetrical alkene. I have a mono-substituted group on this carbon here and no substitution on this over here. And so what we're going to find is that H and Br will add to this in a very specific way. Now to make it work, we need a little bit of a catalytic peroxide. We have a real weak bond right here, and that's what the light will break to give us two free radicals, and then that will allow the reaction to proceed. And what we find is that the hydrogen goes to the less substituted carbon, and the bromine goes to the more, I'm sorry, it's exactly backwards. Bromine goes to the less substituted carbon, and hydrogen goes to the more substituted carbon. And that's for reasons of stability of the free radicals, but we'll see that later. This happens to be called anti-Markovnikov addition, because if the bromine went to the more substituted carbon, that would be what they call Markovnikov addition, which we haven't studied yet. Okay, so I'm showing you all the steps right here for the free radical substitution. Just put them right up front. This is what you want to understand, and that's why I put it on one slide, so that you can see every single step. But we're going to go through and talk about these steps individually in just a little bit. Okay, so initiation requires an input of energy. We're going to use light, but heat is possible. That will split the bromine bond homolytically, so we'll get two bromine atoms, or free radicals. That costs us 46 kcal. But that comes from the light that we're putting in. Now once we get going, the bromine atom is extremely reactive because it only has 7 electrons. And so it's going to come over to the alkane part and strip off a hydrogen plus 1 electron. And that'll make a pretty strong HBr bond. So this bond right here is about 88 kcal. And that's, since it's forming, it's going to be negative. It's going downhill. Depending on what type of CH we have over here, it costs us different amounts. But in this particular example, this is a primary. And primary costs us about 98. So that's an expense. We got to play that plus 98 and then minus 88. So overall, this is not a very good reaction because it's uphill plus 10 kcal per mole. It's a possible reaction, but it's just not going to be real favorable. The only reason this reaction works is because of the next step. You'll notice that HBr looks pretty good, it's pretty stable, but we've made now a primary free radical. So this free radical is going to do the same thing that the bromine atom did up here. It's going to look for something to make a bond with. Now it wants to pay the lowest price possible, and that would be the bromine-bromine bond that we have here, 46 kcal. So if it comes over and grabs a bromine atom, this is the result that we wanted. We want a carbon with the bromine on here so we can do all of those reactions we studied in chapter 9, where we had those bromoalkanes. Now you'll notice also it makes a bromine atom. Well, bromine atom's exactly how we got into this cycle, and so that will come up here and strip a hydrogen off, make HBr, make the carbon free radical. That will come down and grab a bromine atom, excuse me, and then leave behind this bromine atom here, which can repeat again and again. Now down here, the cost was 46. That's real low. That's the weakest bond in the whole system. And then we're making a carbon-bromine bond, which isn't a fantastically strong bond, but compared to what we broke here, it's very, very favorable. Downhill 22 kcal. So if we combine these two steps, which keep going back and forth, every time we cycle through, we're going downhill 12 kcal. If we were running this reaction and feeling it, it would start to get a little bit warm because we're releasing energy. So the cycle together, the propagation sequence, is favorable, minus 12 kcal. Now these free radicals are pretty rare because they're not real stable and they're super reactive. But once we split them apart and they get going, that keeps this chain reaction going. However, sooner or later, two of these free radicals will find each other. Could be a carbon finds a carbon, or a bromine finds a bromine, or carbon finds a bromine. That's what I show here. That's a pure release of energy. So that's going to be a very favorable reaction. And it would kill our chain reactions. Two of them would be stopped cold. However, we're always shining light in, starting up some new ones. And so we reach what's called a steady state, where we're starting off reactions about as fast as we're finishing reactions, and in the middle we're getting this chain reaction cycle going on and on. Now bond energies are a big deal on this because we're always balancing favorable reactions against unfavorable reactions, and so it has to come out in the end overall, favorable. So real important ones are, of course, CH bonds. So if I go down here, you'll see I have a methyl. Now, this is really ethyl, but I'm calling it primary. This is a general pattern, and it's a specific group right here, ethyl. If I have isopropyl, we're going to look at that as a general secondary pattern. If I have T-butyl, we're going to look at that as a general tertiary pattern. And then I have the allyl pattern, where I would have a free radical next to a pi bond, I have the benzyl pattern, very similar. These are pretty stable free radicals. And then I have vinyl. So vinyl is a tough one because that's an sp2 carbon, and we're stealing an electron away from that. And we already know that sp2 is more electronegative than sp3. So that's actually kind of a high bond there, bond energy. And then phenyl is very similar to vinyl. It's going to be very hard. And surprisingly, hydrogen attached to hydrogen is a very, very strong bond. Even though they're just two little tiny atoms, it's 104 kcal. So that's a pretty super strong bond there. Now, if I go across here, we can look at other possibilities. So here I have methyl attached to methyl. So we're looking at the carbon-carbon bond here. Methyl attached to ethyl, methyl attached to isopropyl or secondary. This would be primary. And so we can go across and see all those bond energies. Those aren't going to be so important to us in this topic, but they are important bonds to be aware of. And you'll notice there's little differences there. And so hopefully you can understand why they're different. If I have a methyl and a methyl, and I'm making two free radicals, those have no inductive effects. However, if I have an ethyl as one free radical and a methyl, this would be a methyl free radical, not real stable. But with the ethyl, I have one inductively donating R group, so that makes it a little more stable. Okay? And then we get out here carbon fluorine, carbon chlorine, carbon bromine, carbon iodine, and different substitution patterns have slightly different bond energies. Okay, they're big in hydrogen, less different in terms of the halogens over here. And the family that's going to be most important to us will be the bromine, because we're using bromine molecules to make bromine atoms to do the substitution, because it comes out with the best result, most selective and possible. So this column right here is real important. I put that one in blue. And this column right here is real important. I put that one in blue. If we come down and look at the actual halogens, they're all really weak bonds. Okay, so I have fluorine connected to fluorine. Fluorine hates that because fluorine's so super electronegative. It wants to bond to things that give up its electron density. And another fluorine is like the worst possibility. Chlorine's pretty weak. Bromine's pretty weak. Iodine's pretty weak. These are also getting real big when you get to iodine, so the sigma bonds are just a very weak bond. Again, the only ones that will be important to us at all will be the chlorine and the bromine. We'll use chlorine as a contrasting example with the bromine, but mainly we're interested in bromine. Okay? So if I come up here and just consider the carbon-carbon bond strength, okay? So I say, what is this bond energy? So if I came down here and looked at this, you would have to find what's on this side. That's a methyl. And what's on this side, that's a primary. Okay, so I mentioned it before. Here's methyl, and ethyl would correspond to the primary. That would be 86 kcal. If I look at number 2 here, this is a primary attached to a primary. So I'd have to come over, here's ethyl, that's a primary, attached to an ethyl, that's a primary. You see it's a little cheaper, it's 82. And that's because I have an inductive effect on each carbon there from the extra methyl, so it's a little easier to do. If I come down here and look at 3, this is a vinyl connection to a primary. So I'd have to go down to vinyl. I'd have to go over to ethyl primary right here. That's a really strong bond because I'm asking to take away an electron from an sp2 carbon. However, if I look at this one, this is an allele position with a methyl. The methyl's not so great, but allele's pretty good. So if I look at this, I would have alleles right here. And if I look at methyl, look at how low that is, 74. Because there's going to be resonance, stabilization of the free radical on the methyl part there. And just another couple bonds here. If I have a CH right here, I'd have to decide what kind of carbon. I see 2 carbons attached. That's a secondary carbon. So I'm looking for a secondary carbon. That would be isopropyl. Attached to H, that would be 95. Okay. And then if I look at this, this is a primary carbon attached to bromine. So here's bromine, primary would be right here, that would be 68 kcal. Okay, now the bonds that are going to be important to us again are going to be the bromine-bromine bond, down here 46, and then all the CHs, that'll be all these guys over here, and carbon-carbon bonds, there's a whole bunch of them here, but we're not going to really consider those. These are the most important. And then as products, we're making HBr in the free radical substitution. So HBr would be down here at the bottom, go over to here, that would be 88. That's specific, that's unique. But then carbon-bromine has all kinds of possibilities depending on the substitution pattern of the carbon. Okay, so we're going to put in light, and so what we're sort of wondering is, why does the bromine bond break? Why does it react and not these other bonds over here? And so we will look back at the table. Remember, bromine is 46 kcal. Okay, so it makes sense that the first bond to break will be the weakest bond. So if we looked at the carbon-carbon bond for, say, ethane, that's 90 kcal. You can see that's much stronger than the bromine molecule, so that's not going to break. And then if we look at the CH, this is a primary CH, that's 98. That's even stronger. That's not going to react. So it makes sense that this is the first thing to react. Now remember, this is a very simple mixture. We have bromine molecules and a hydrocarbon, in this case ethane. I picked ethane because it's so simple. There's only one kind of CH, even though there's 6 hydrogens here. They're all equivalent. Okay. So initiation, as I said before, that's our first step, and that's relatively rare because mostly when we shine in a light and break this bond, mostly they just rejoined. Okay, they're right next to each other, they're super reactive, and so they just join back to the molecule. However, there's lots of alkane around, and if an alkane molecule gets bumped in between, then these guys are isolated, and they can go off and start 2 different chain reactions. Okay, so what did that cost us? That cost us the input of light and the 46 kcals that it took to break that bond. Okay, so now we have 2 free reactions running around. We're just going to look at them at one. So I have a bromine atom, and it has to figure out what to do. Now, it could react with a bromine molecule, but that goes nowhere. Okay, that just duplicates what we started with. So I have a bromine atom, and it's going to come over and react with this alkane. Now, I deliberately picked this alkane to be simple, so there's only one kind of CH. We don't have to consider that yet. And we're not going to attack the CC bond. We could consider it, but it's not as productive. So we're going to take off an H. And that's going to make HBr, which liberates 88 kcal, helps to somewhat compensate the expense of this bond energy, because primary CHs are pretty strong. So that's going to go uphill 10 kcal. By itself, this wouldn't work. And we make a new carbon-free radical. So this carbon-free radical is going to have to decide what to do as well. If we looked at this as in terms of an energy diagram, what we call potential energy versus progress of reaction. So over here I'm looking at how does the energy change as the reaction proceeds. Okay, and so these guys would counter each other, strip off the hydrogen. We're going to go way uphill in energy, about 10 kcal. And so we would be sitting up here at this higher energy point. If we were to calculate a K equilibrium, we could do that with the 10 to the minus delta H over 2.3 RT. That comes out, pretty small equilibrium right here. So, 10 to the minus 8, 10 to the minus 7, we're up here. So not much product if this is all we're looking at. However, if we add in that second step, 2B, now the carbon-free radical comes over and strips a bromine out, bromine atom, leaves behind a bromine-free radical. This is really favorable because it only costs 46 to break this bond, but we gained minus 68 by making this bond, which is the actual product that we want. Okay, so overall that's minus 22. Now if we put these 2 steps together, we'll see that plus 12 and minus 22 is going to be very favorable. Now in this K equilibrium, if we calculate delta G over 2.3 RT, comes out 10 to the, close to 10 to the 16th. So this is going to be hugely favorable and more than compensates. Anything that we can get up on that first step is immediately going to go on to product here. And so we cycle in a controlled, selective way to the product that we're looking for. Okay, now this energy, potential energy versus progress of reaction diagram is much different. This is way, way, way downhill. Okay, and gets us to a point that started the whole reaction over. So that's our chain reaction part right here. This will go on, say, hundreds to thousands of times per cycle. Okay, so once we get a bromine atom, then we're going to make a whole lot of product until we get to that termination step. All right, so termination is 2 radicals find each other. We'll consider 2 of them are dead ends. So if we go over here, the carbon-free radical finds the bromine atom. That makes a stable molecule that's not going to change under the reaction conditions. The bond's too strong here. If the carbon finds the carbon, it's going to make a strong carbon-carbon bond. That's not going to change because it's too stable under the reaction conditions. If bromine finds a bromine, It stops two-chain reactions, but not really, because we're still shining in light. And this can just re-rupture and go back to bromine atoms until we use up all the bromine. Okay? So this is not, I would say this is not really a termination step. These guys are up here. And in fact, we won't really emphasize the possibilities here. We'll just use two carbon-free radicals, say the carbon group and a bromine, and that'll be the termination. This is hugely exothermic, okay, because there's no barrier. These are both super high energy, super reactive, and making a stable product. Okay. So overall, the propagation is the thing that we really want to look at. So if we look at the potential energy versus progressive reaction diagram for both steps together, what we see is we start off with this bromine atom, grabs a hydrogen, we go up 10 kcal. So we're up a little higher, not real favorable, looks like, except as soon as we get here, that grabs a bromine atom, goes way downhill in energy, and makes the bromoalkane that we're looking for. At the same time, it makes a bromine atom, puts us back over here, and we cycle through again and again and again. And so the overall for both steps is going to be a potential energy of minus 12 kcal. It's going to be very favorable. All right. Now, we're pretending like once the alkane reacts, we just get one bromine on. But in fact, as soon as we start making this, it can react itself. And so it can react a second time, and it has two choices, the carbon with the bromine or the methyl on the other side. And so we get two possible products. These could each react again for a third bromination, and that would give us two possible products. The third bromine could come on at the same carbon here, or one of these other two. And then these could react again to give us four bromines on there. And that would give us two possible products. And then each of these could react again to the identical product of 5 bromines on there. And this could react again to give us 6 bromines on there. And when there's all bromines at every single position, we call that a per something. Per bromo, per fluoro, per chloro. In this case, ethane. Okay? So these are all possible products. Some of these might be desirable in other situations. The only one we're really interested in is the monobromo, and we will also look at the dibromo down here, okay, for making alkynes. But right now, we're just looking at the monobromo one. Now, if you wanted to get the per bromo product, then you just load up with bromine. Okay, so you have a lot of bromine per ethane, and it just keeps reacting and reacting and reacting. If you only wanted the monobromo, we could put in a lot of ethane and a little bit of bromine, and then we try to take off the monobromo product right here. We could do that maybe some in continuous synthesis mode that would take that away. But in our course, we just have to say one equivalent of bromine, we get the monobromo product. That's the way we'll look at it. If we wanted 2 bromines on, say this one right here, we would put 2 equivalents of bromine, and that would give us this. Our reactions are all pencil and paper, so we don't have to worry about the complications. Now I put on here the other halogenations, just to show you the difference. These are all on the same size energy scale. You can see the one with the fluorine. Fluorine makes such a strong bond with H, okay, that it's just going to be very, very exothermic, 38 kcal. And then if the carbon-free radical abstracts a fluorine atom, that's 70 kcal. Each time we cycle through here, that's 108 kcal. This is so super exothermic that you'd have to control this reaction. Okay, if it got going, it would just get out of control and you'd have an explosion. It would just blow up. One way to do that would be, say, to use some inert gas, like argon, to dilute it down so that the heat was dissipated mainly into the inert gas. If we look at chlorine, that first step on chlorine is actually exothermic, and that's sort of the problem. Remember, on the bromine reaction, the first step was endothermic. It went uphill in energy, and that sort of slowed the reaction down and made it very picky and selective. Whereas chlorine, it's exothermic on the first step, and it's exothermic on the second step. And so that makes it not so selective. It's not a problem in ethane because we only have one kind of H. But if we get molecules that had a lot of different types of H, then we get a distribution of products, which isn't yet generally what we're looking for in a synthesis. Bromine looks pretty selective. It goes uphill and then it comes back down more, so it's actually a workable reaction, but real picky on that first step, which is good. Iodine is way uphill in energy because to make the carbon-free radical is so much less stable than the iodine-free radical. And so it's way uphill, and then it doesn't come down enough to make the reaction favorable overall. So each time we cycle through this, we're losing energy. We're taking energy out of the system right here. So actually the delta H is a plus 10. So it's a sluggish reaction. Doesn't really work that well. So we don't propose that one. This is our reaction right here, the bromine. And this is why, when you look at all these possibilities. Okay, so fluorination, explosive. Too much energy is released too fast. Chlorination, very reactive, so it's not real selective. It's workable. So we can chlorinate things. This is okay reaction. Industrially, this might be a useful reaction. Bromination in the lab, this would be probably our best choice right here. Selective, which is a good thing. And then iodination is just too endothermic, doesn't really work. So bromine is our guy. Now, picking off the CH is the super important part of this. That's going to determine how the reaction works. And so I posted right here the CH bonds. And I put a little H here because this is the H that's being lost in the cases that I'm looking at in these energies over here. So this would be a methyl. Methyls are a little bit expensive because we're left behind with a methyl free radical, which doesn't have any inductive effect, helping that electron deficient carbon. We'll talk about that in just a minute. If I have a primary, I got a little bit of inductive effect from one R group, and you'll see the bond energy goes down. In each case, H is being lost, so that's not the different part. The different part is the carbon part that we're looking at here. If I look at secondary, I got two inductive effects helping the free radical, so it makes it a little cheaper. If I look at tertiary, I got three inductive effects helping, it makes it a little cheaper, 92 kcal. And then if I look at allylic, I have resonance. So even though this is primary, which we would think up here is going to cost us 98, I have that adjacent pi bond helping stabilize it with resonance. So it's 86, a lot cheaper. And if I look at benzyl, again, it's cheaper because of resonance, the adjacent pi system. This is called an acyl CH right here. So if I had an acyl CH, it turns out that's pretty weak. That's 86. If I have a vinyl, this is a super high energy, jumps way up to 110. That's about the same for a phenyl. They're both very, very expensive, hard bonds to break. If we look at SPCH, that's even worse because that's not SP, 50% S, and you're stealing an electron away. That's going to be super hard, and we're not going to propose these. We won't even propose this one right here. Okay, so we're pretty much going to stick to these top groups right up here. All right, so remember, homolytic, each guy gets an electron. A gets one and B gets one. And so that's what we're looking at over here. Always one of our atoms here is an H, and then the other part, say the A part, is the carbon. Okay, so we won't worry too much about this. Okay, CH bond energies, that's the choice that has to be made. So we have a bromine that'll be sitting here. It's going to come over and abstract an H, that'll make an HBr, which we said was minus 88. And then depending on the substitution pattern of the carbon, which primary is 98, secondary is 95, tertiary is 92, you can see why tertiary would be more favored, because it only cost us 92 kcals. Remember, this is the expense over here, and this is the gain that we get. So in our first example, we were just using ethane. Everything was primary. All 6 hydrogens were the same. But now we're going to start to look at other molecules that have a variety of choices, a variety of possibilities. Okay? Now we could design a molecule that had both choices in one molecule. So propane has a choice of picking off a primary on either end and a secondary in the middle. So if it picks off a primary, we got to go up 98 kcal. Okay? And then we got to compare that to the choice of the secondary, which only goes up 95 kcal. So that's 3 kcal per mole difference between those two. That's a lot of energy. Remember, the energy part is what shows up in the exponent. And so it's not quite a factor of 3 because we have that 2.3 RT, that 1.4 kcal. But you can see it's going to be something significant in the exponent. And so it's going to be much more selective for secondary. we could design a molecule that has the primary versus a tertiary. So notice I got 9 primary positions and 1 tertiary position. So you might think, well, all that concentration effect of 9 to 1 might make the primary favored. But remember, there's a difference of 6 kcal up here. Here's tertiary, 92, primary, 98. Difference of 6 kcal. And remember, that's an exponent part. So even though I got 9 of these primaries, they don't stand a chance against that tertiary because of that big energy difference. Okay. So the ones that we're interested in be methyl, be 105. This, even though it's 105 and expensive, there's only one kind. A methyl is a methyl. And so this would work on a methyl. Just it has no competition to go against it. Primary, 98. Secondary, 95. Tertiary, 92. Allyl, very, very reactive, even though it's primary. And vinyl, very unreactive. Okay. So this is what we're looking at in that choice. The bromine atom has to make a choice. And if it's got weaker bonds, it will choose those more selectively than stronger bonds. Okay, we always make the same guy, minus 88, and then a carbon-free radical. So if we come down here and look at chlorination and bromination, remember the first step on chlorination is actually exothermic, so not so selective. If I look at tertiary versus secondary versus primary, tertiary is favored, but only about 5 to 4 on secondary, and 1 is the reference point. So if we looked at primary as a reference, secondary would react 4 times faster, and tertiary would react 5 times faster. Not a great degree of selectivity here. Okay. Now if we had allylic and benzylic, that's quite a bit different when we look up here. And so there is a little bit of selectivity there, but not a whole lot, even among themselves. So tertiary allylic is about 100 times better. Secondary allylic is 70 times, and primary allylic is 20 times. Remember, our reference point is just a simple sp3 primary that we're looking at. If we come over and look at bromination, much more selective. So here's tertiary. It's about 1,600 times more reactive than a primary. And the secondary is about 80 times more reactive than a primary. And if we were to put in the tertiary or allylic, a tertiary allylic benzylic, about 1,000,000 times. So you can see the allylic and benzylic are super reactive, even over the tertiary up here. But mainly we're going to stick to these guys here pretty much. Okay. And then we're going to consider vinyl and phenyl, that they don't react. They're just too slow. So why do we have this effect? I've mentioned it a couple times, but I actually have it explicitly shown here. If we consider a methyl free radical, it's not a great free radical, but it's possible from methane. Okay, but if we compare it to, say, a primary free radical, and that could be just from an ethyl free radical, but more generally this would be primary, we have an inductive effect. This is an electron deficient carbon. There's only 1 electron here. It's sort of like the carbocations that we talked about earlier. I have those shown down here. And so when we have an electron deficient carbon, it really helps to have an electron donating group, an inductively donating group. And so this carbon has additional electrons that all can be polarized towards this electron deficient center. So here it's an electron deficient free radical. Down here it's an electron deficient carbocation. You can see this is much more electron deficient because I don't even have that 1 electron up here. This has a charge on it, +1. This is neutral, but only has 7 electrons. So both of these benefit from an inductively donating effect of an R group. Okay, but the carbocation does it much better. So if I look at carbocations, methyl versus primary, that extra R group stabilizes by 35 kcal. If I look at the free radicals, that extra R group stabilizes by 6 kcal. Okay, because it's not totally naked. It has a single electron there. And then if I add another R group, it comes down about 20 kcal from the primary to secondary. Remember when we did SN1E1, this was the first place we could actually start to get reactions to occur. We did not propose methyl and primary carbocations, but we did propose secondary. And then tertiary was 15 kcals per mole, more stable. If we come over and look at free radicals, it's in the same direction, but not as extreme. Okay, so the methyl free radical, it's 12 up here relative to our reference point of tertiary, and then a primary is 6 kcal, and secondary is 3 kcal per mole, more stable than the tertiary, less stable than the tertiary. Okay, so tertiary is most stable in both cases, and secondary, primary, methyl. It's possible all of these can form with free radicals, but we only propose tertiary and secondary free radicals, carbocations over here. Okay, so when the atom comes over and picks this off, that's going to give us different stabilities of carbocations. But there's another effect we can invoke besides the inductive effect, and that is if these groups are all carbon groups, they're bigger than a hydrogen. So there's a steric effect. If this is sp3, they're all jammed together with 109-degree bond angles, and that's going to make them a little crowded if they're all carbons. If I pull this hydrogen away, this will spread out to what's called an sp2 free radical, and these big R groups can get farther away. So that's a steric effect that also favors tertiary over secondary over primary over methyl. Okay. So we also have resonance stabilization, which we've mentioned, but we'll just point it out here. So if I have a primary, we said that's 98, that's a certain amount. If I put on 2 R groups, that makes it better inductively. If I put on 3 R groups, that makes it better inductively. And so these are easier free radicals to form. Now if I come down and look at this is a primary free radical, but there's an adjacent pi bond. So if I make a free radical here, saying down here, I can write a resonance form where I put the free radical over here, and I can do the same thing with a benzyl, because I got these adjacent pi bonds. And so that makes them much more stable than expected, by quite a bit. Because this is primary, but this is primary with adjacent pi bonds, and same here for the benzyl. And so these are much more stable than we expect. We have the inductive effect, tertiary better than secondary, better than primary. And we have the resonance effect, where the adjacent pi bond makes it better than the primary over here. Okay. So I actually drew these out 2D and 3D. 2D, we'd have to remember each electron gets an arrow in free radical chemistry, so it's a little more complicated to show that. So I'm going to bring this electron in, borrow this electron, and make a pi bond here. And that leaves the free radical on this carbon. So that spreads out the electrons, spreads out the unstable free radical. This is 3D. The only way this works is if these orbitals are parallel, and so that's why I like to draw the 3D as well, so that you can see that nature that we have there. Okay, so I borrow the electron, make a pi bond here, and then leave the free radical at the other end, and that makes it more stable. And we can do that with the benzyl as well. So we spread the free radical throughout the ring at what we call the ortho and para positions that we're looking at. And notice each time I do that, I have 3 arrows. And notice that the arrows always are half-headed arrows, or what we call fishhook arrows, because we're only moving 1 electron. If we move 2 electrons, then we use a full-headed arrow. Okay? And so we're going to end this as the first part of our free radical chemistry, and then I'll do a couple more lectures on this. The last lecture is going to get into synthesis a little bit, and that's a little bit challenging for beginning organic students. Okay, so see you then.